This is the third lecture on Fourier transform. In the earlier lecture, we have discussed about the Fourier cosine and sine transforms, which are applicable respectively to the functions having even and odd parity. And thereafter, we have discussed what is the Fourier transform of delta functions in K space, in position basis in K space, as well as in time and frequency domain. And we have also studied the property of Fourier transform in 3 dimension. Today we shall discuss the properties of Fourier transform, but before going to that, let me first introduce recall the definition or notation we have used. The Fourier transform of a function x is known as a of k, and we have the properties that is, let me first write the defining property of this is in 1 dimension. It is a of k is equal to 1 upon root 2 pi f of x. And the inverse transformation is given by f of x This is the Fourier transform pair. First we come to the linear property. Property number 1 is linear property. That means if we have a function f of x, if f of x itself is a combination of two functions like this, then as per the statement, this is C1 A1K plus C2 A2K, where A1 is the Fourier transform of F1x, AI of K is the Fourier transform of Fi of x. To prove this, the proof is very trivial. So we write this one, this laser is equal to 1 upon root 2. Then integration, I am not writing the limits, it is always from plus infinity to plus minus infinity. If we use any other limit, I will inform you. Then this is C1 F1 of x plus C2 F2 of x e to the power minus I kx dx. Since c is constant, we can take it out of the integration sign and write it as 1 upon root 2 pi integration f1 of x e to the power minus I kx dx plus c2 1 upon root 2 pi f2 of x e to the power minus I kx dx. As for definition, this is the Fourier transform of f1, that is a1. So this result is c1 a1k plus c2 a2 of k. Hence the result is proved. Now come to the this is the linear property. Now, shift of scale. Second property is the shift of scale, that is what happens if we change x by some scaling factor, scaling property. We have Fourier transform of f of alpha x. What will be the relation in terms of Fourier transform? Let me first, so that dx. This we write as f of alpha x e to the power minus I k alpha x by alpha, and here we write d of alpha x, and to adjust we write 1 by alpha over here, and we use 1 by alpha f of y e to the power minus I k by alpha y dy. So this is the Fourier transform of f mediated by k by alpha. So the result is 1 by alpha a of k by alpha. This is the scaling property. Here we have assumed that f and a are the Fourier transform of each other. Now coming to the shifting property or translation. Here what we do, we consider the function as a function of x plus minus c. What will be its Fourier transform? So let me start with this. F of x plus minus c. This is 1 upon root 2 pi integration f of x plus minus c e to the power I k x plus minus c dx. You see that e to the power, this part can be taken out. So we take out e to the power plus minus I k c, and the rest of the thing is this is this result, and we want to change it into this form. This is the basic definition, and then we do one thing. We use this root 2 pi, then integration f of x plus minus c. We introduce here, it is minus, it was minus, because in Fourier transform it was a minus sign. So it was minus I k x plus minus c. So we have adjusted a term that has to be compensated, and we write e to the power plus minus I k c, and this is dx. We write it as e to the power plus minus I k c f of y e to the power minus I k y and dy. If we add d of x plus minus c is equal to dx, so this do not undergo any change, and this 2 pi factor is there, so this is e to the power plus minus I k c a of k. This is the translation property. Now coming to the fourth property, that is the when it is multiplied by, the function is multiplied by exponent, the exponential multiplication. This means the function f has been multiplied by e to the power alpha x plus minus alpha x and f of x. This is what will be its Fourier transform. Let us start that f then we write it as 1 upon root 2 pi integration e to the power plus minus alpha x f of x e to the power minus I k x dx. This part is coupled with the f of x e to the power minus e to the power minus k. This is alpha x. If we have plus, then this minus minus plus, so it is plus minus x dx. So the result is, this is the Fourier transform mediated by this kernel. So this is a of k plus minus I alpha. This is the Fourier transform modulated by this or this kernel. So it is a k plus minus I alpha. Now coming to the modulation property. Modulation property means the function is multiplied by a sinusoidal wave. So here there will be two statements. One is function f is cos alpha x f of x. So let us consider the Fourier transform of this. F of cos alpha x f of x, this is equal to 1 upon root 2 pi integration cos of alpha x f of x e to the power minus I k x dx. Now we write this as, let me write first. Dx. So what happens? Oh, sorry, e to the power ikx is missing. E to the power minus ikx dx. Now we can couple this one with, note the change, this sign should be plus. Root 2 pi. F of x. When these two are couples, we have e to the power minus I k plus alpha x, and when these two couples, we will have e to the power minus I k minus alpha x dx. So first thing is the Fourier transform of f mediated by this kernel, and second one is this kernel, and so the result is, and in Fourier transform this part is absorbed, so leaving behind 1 by 2 a of k plus alpha plus a of k minus alpha. So this is similarly you can consider the modulation by sine function. If it is modulated by sine function, then we will have sine of alpha x, and sine of alpha x can be written as sine of alpha x this is sine of alpha x, so we write it as, now I am indicating the changes as we go from sine modulation by sine to cosine. The changes is this, here we have changed sine function, here we have changed sine function, and then it is e to the power minus thing. So this is minus, this is plus, and this is 2i there. If we take I on the numerator, there will be a minus sign, so it will be a of k plus alpha minus a of k minus alpha by 2. This is the modulation when mediated by the sine function. So we write another modulation function is as this: Fourier transform of sine alpha x f of x is equal to I times a of k plus alpha minus a of k minus alpha by 2. This is the modulation property. Now we consider the symmetry property. The symmetry property means The symmetry property is that it deals with the Fourier transform of A of x. A of x. Now we know the definition of A of x. This is the definition of the symmetry property relates the Fourier transform of A of x. Before going further, let me first write what is A of k is this. Then A of k, we know that it is this definition. Then A of x is obtained by interchanging x and k. This is obtained by interchanging between x and k. So this is the result. Now we are to find out the Fourier transform of this. So this is dx. Now we see that this is f star f of minus k. This is f of minus k. So the symmetry property is that minus k. Now the next property is the conjugate property. Conjugate property means it relates the complex Fourier transform of complex conjugate of a function. Thus it deals with the f of f star of x. We start with this. A of k is equal to 1 upon root 2 pi f of x e to the power minus I k x dx. If we take the complex conjugation, this is actually the Fourier transform of f of x. If we take complex conjugation, then we get a star k, and on the right hand side we will have 2 pi f star of x e to the power plus I k x dx. This is simply a of minus k. A star of minus k. This is equal to a star of minus k. Now the important relation, the convolution theorem. Let me first write the theorem, then I will coming to the explanation of it. Convolution property, or this is called convolution theorem too. If we have two functions, then we have function 1 and function 2, both are function of x. Then the convolution of these two is, so if you have two function f1 of x and f2 of x, then the convolution of f1 f2 by definition of f1 and f2, which is denoted as f1 star f2 and is defined as f1 star f2 is equal to 1 upon 2 pi integration from minus infinity to plus infinity f1 at t, f2 at x minus t integrated over dt. This is the definition of convolution. Actually, this quantity arises from the measurement point of view. If we want to measure any quantity, then this quantity, the measurement of this quantity is affected by the error in the measurement of the quantity. The convolution actually takes care of this. This inaccuracy in the measurement. The statement is that Fourier transform of convolution of two functions f1 and f2 is simply a1k times a2k. This is the theorem. Now, so for proof is concerned, we come to this part. Here I am trying to prove the theorem first. Now, Fourier transform of f1, convolution of f1 f2 is equal to 1 upon root 2 integration of dx. The f1 f2 are the functions of x and the, let me write the functional form. Okay, f1 star f2. Then we use the definition of convolution. This is 1 upon root 2 pi. One root 2 pi is here, another is here, so it is root 2 pi. Then this integration over x from minus infinity to plus infinity with the factor e to the power minus I kx. Now we come to this part. This is integration over dt from minus infinity to plus infinity. f1 at t, f2 at x minus t. This is the form. Now, now we first write this 1 by 2 pi. We rearrange the integrals and we write dt f1 of t. Then we write integration over dx f2 x minus t e to the power minus I kx. Now we can use the shifting property. There is shifting property, that is when we do this, this is nothing but, if we take root 2 pi from there, it is a2 of k and there will be e to the power minus I kt. So we have used the shifting property, third property has been used over there. So the 1 root 2 pi goes with a2 and we are left with only 1 root 2 pi, and the quantity is dt e to the power minus I kt f1 of t. This multiplied by a2 of k. Since the integration left is over t, we can take a2 of k out of the integral, and this part is a1 of k, so the result is a1 of k multiplied by a2 of k. This is the convolution theorem. Parseval's relation, then come to the Parseval's relation. This is the generalization of Parseval's theorem, and the statement is this is convolution of f1 star f2 is equal to a1k a2k. The ninth property is Parseval's relation. Parseval's relation says that if f1 star f2 or f1 of x f2 star of x dx is equal to integration over k Earlier we have used Parseval's theorem for the modulus of a function, in which case f1, f2 are the same function, and on the right hand side we get this modulus of x squared dx is equal to modulus a of k dk over all space. That was the Parseval's relation we have obtained earlier. Here the Parseval relation, it is just a generalization of Parseval relation, which is applicable for two different functions. Now coming to the proof, we know that f1 can be written as f1 of x can be written as 1 upon root 2 integration over a of k e to the power plus ik x dk, and f2 star of x can be written as similarly here we have used the two dummy variables. The variable that is being integrated out is called the dummy variable, and we have used two different dummy variables, so that the left hand side, there is a sum of, and all the sum are from plus infinity to minus infinity. So this is 2 pi integration over dx integration over dk. Sorry, it is a1, this is a2. Integration over dk prime So what we have done, in the left hand side there was already an integration over x. So this is the integration over x. Then we have replaced f1 by this relation. So 1 by root 2 and on this. This is for f1 and this is for f2. Now what we do, we first carry out the x integration. So one, then we will have 1 upon 2 pi, this 1 upon 2 pi, integration over dx e to the power I x k minus k prime. You see that e to the power I kx comes from there and minus kx. This all together is delta k minus k prime. So the result is when we perform this integration, it will be, the result is a2 star at k. So the result follows. This is the Parseval's relation. And last property is the Fourier transform of derivatives. This says that if we take the Fourier transform of the derivative of a function mediated by k, this is ik times a of k. Let me prove this. And by this we will cover a lengthy journey through the properties of Fourier transform. So we know the Fourier transform of f of x is equal to a of k is equal to 1 upon root 2 pi f of x e to the power minus I kx dx. So the Fourier transform of a prime of x will be coming to this definition. So we integrate it by parts. So first thing is that we integrate this. So it is f of x times the second function remains unchanged I kx from minus infinity to plus infinity minus integration of first function derivative of the second function. So here we will have minus ik e to the power minus I kx dx. since the function we are considering should be integrated over all space, that is, the function should have a property that f of x dx from minus infinity to plus infinity must go to 0. So this function at plus minus infinity must go to 0 to make the integral 0. So this part is 0. So we are left with this is minus plus. There is a sign change. This is first part minus sign, and Fourier transform there from a minus sign. So okay, this is plus, so this is plus ik, and the rest of the thing, when we couple this with this is the a of k. So this is the result. Now if we find that what is the Fourier transform of double derivative of a function, we get that it is ik times first derivative of the function, and then we will have ik square derivative of the function. Sorry. So this is equal to minus k square a of k. In general, if we consider the nth derivative of a function fn of x, this is n, then it is ik to the power n a of k. This property is very helpful in solving differential equation using the Fourier transform technique, which we shall come to after the completion of differential equation.